we're going to start with some plate tectonic lessons. In fact, I had a couple of emails this past week with some follow-up plate tectonic questions from last week. So we'll go ahead and start there and help us understand the Cascades itself. Let's start with kind of a review, I suppose, if you've been with us a number of times. Let's see, how am I going to do this? Yeah, right, that's the plan. I'm going to do this. So we need some music here, I suppose, while I'm drawing. I want to draw a plate tectonic cross-section. Let's put a boat in here. Let's put North America moving west. We know that, right? This is an underwater mountain range called, let me label it properly for you, called the East Pacific Rise. And those of you that know basics of plate tectonics, you've heard maybe about the Mid-Atlantic Ridge, which is an underwater mountain range that was discovered right down the middle of the Atlantic Ocean back in the 1950s and early 1960s, which really helped us understand this whole plate tectonic business. That was one of the keys to unlocking that whole mystery. Well, the Pacific Ocean has a similar underwater mountain range that is very active, meaning that magma is coming to the surface from the asthenosphere and is creating crust on the ocean floor, and that crust is spreading away in both directions from that underwater mountain range, just like the Mid-Atlantic Ridge in the Atlantic Ocean. But this is not the Atlantic, right? This is the Pacific Ocean, and this is North America, and I'll put Westport down there, which is our coastal community of reference. However, this is going to be a picture 200 million years ago. Okay? More on that in just a second. Let me draw the same thing on the chalkboard here. Now, why would I draw the same thing? I want to draw the same thing, but I want to draw a map. Instead of a side view, I want to draw a map of the same view. And I'm going to do this, and then I'm going to do this. Okay, what is this? So this is North America. Now we're looking down from heaven onto North America, moving west. And what is this zigzag pattern out here? It's the East Pacific Rise, the EPR. And coming away from the East Pacific Rise are these arrows showing what? Showing movement of the ocean crust, movement of the ocean floor in both directions. And the East Pacific Rise is broken by some San Andreas Fault-like faults. So these are actually some plate boundaries here separating that. Okay, this is also 200 million years ago. Now, 200 million years ago is famous in the history of our planet because a large supercontinent called Pangaea started to split apart 200 million years ago. And for the first time, North America started moving west. And by God, North America is still moving west, 200 million years later. But here's the first message of tonight's lecture. The distance between Westport and the East Pacific Rise was a hell of a long way 200 million years ago. And now, it's not that far. In other words, the North American plate has been slowly inching closer and closer to this stationary East Pacific Rise over the last 200 million years. And why are we talking about this tonight? We're talking about it tonight because there is not only earthquakes generated at these subduction zones, but there are beautiful cone-shaped volcanoes coming right up from the subducting plate. So here's a concept for you. These X's are beautiful cone-shaped volcanoes, erupting material. Mount Rainier are like mountains that are erupting volcanic material. We had an intact, beautiful chain of volcanoes all along our west coast 200 million years ago, stretching from Alaska down through British Columbia, down through the Pacific Northwest, continuing all the way down through Mexico. Beautiful, intact chain of active volcanoes 200 million years ago. Similar to what continent today? South America today has a beautiful chain of volcanoes going down the east coast. Excuse me, the west coast. Those are the Andes, right? Okay, so we had the same thing. We had an Andes-like kind of complete, intact chain of volcanoes 200 million years ago. Okay. What are we going to do to these diagrams? We're going to flash forward to today. Okay? And to do that, I'm going to remove 200 million years ago. I'm going to remove most of that plate, which I didn't label for you, but I guess I'll just tell you what the name was in case you're curious. It's the name of Pharaohs Plate. Oh, heck, I should write it. Since it's on the test tomorrow, I should write it. There is an exam tomorrow in my Geology of National Parks class, and I had a lot of visitors to my office this afternoon. Lots of hand-wringing, a few tears, lots of problems, okay? So we tried to solve it. Okay, so that Pharaohs Plate, this dominant plate of the planet 200 million years ago, the monster plate has been slowly reduced in size. Why? Because we're going to move this boat, we're going to move this continent closer and closer to the East Pacific Rise. Until today, we have a more familiar picture. The picture that we had on the board the last couple of weeks when talking about earthquakes. What do we have here? North America. Here's Westport. Beautiful penmanship. And this is not the Pharaohs Plate anymore. What's the name of this plate? That's right. It's the Juan de Fuca Plate. So here's a little secret. The Juan de Fuca Plate is just a new name we have for what's left over of this thing called the Pharaohs Plate. In other words, the Pharaohs Plate is the ancient plate that is responsible actually for much of the geology of the west coast of North America. And this last little piece that's still hanging on, and the distance between Westport and East Pacific Rise, not very much, that's what we've got here. It's a remnant. North America has gotten closer and closer to the East Pacific Rise. Okay, I'm going to change this a little bit, but I want to do the same thing here. I want to draw a picture today. Oh, heck, I'll do it over here. So let's pretend this is North America now that's moved away. Oh, I should do it. We shouldn't pretend. I got to do a complete job here. Now notice a couple of things. This is today, same as what we have over here. Here's the Juan de Fuca Plate coming at us. And by the way, I'm being coy about these arrows. More on that in a second. These are the Cascade Mountains. We have 17 active composite cones, or cone-shaped volcanoes, that are actively erupting. Why? Because the Juan de Fuca Plate is next door subducting. Here's the important point. Notice that we don't have any X's in Central and Southern California, where we used to have them. Why don't we have those volcanoes anymore? The answer is North America has started to cross over the East Pacific Rise. The East Pacific Rise further south has literally slipped beneath North America, and now we have the Pacific Plate moving towards Japan in interaction with the North American Plate, and the result is the San Andreas Fault. So, if you've been to the Sierra Nevada mountains in California, Yosemite National Park, Kings Canyon, Sequoia National Parks, beautiful, right? That's where the volcanoes used to stand in eastern California. And there has been a complete transfer of power from active volcanism in California to now uplifted mountain range made out of complete granite. Granite that was actually formed underneath the volcano. So the volcanoes of California have been erupted, and now this underground magma has solidified and come to the surface. Why am I getting into this? We're talking about Mount Rainier tonight. One of the questions that I added on my email to you to try to entice you to come this evening, that was creepy. One of the questions was, are we always going to have Mount Rainier on our western horizon on a beautiful bluebird day like we had today? The answer is no. And I hope that you can see why. This has been a very slow, gradual process of destroying the Pharaohs Plate, now called the Juan de Fuca Plate. And the job is not completely done. I give it 5 million more years. $5 million more years. If we come back, we can magically come back 5 million years from this evening, I'm of the belief that North America will have crossed over the East Pacific Rise here, just like it has at points further south. And that means our volcanoes, Rainier, Adams, St. Helens, Baker, Glacier Peak, and down further to the south, Jefferson, Shasta, Hood, Lassen, they're all going away. And taking their place will be magma that is presently underneath those volcanoes, solidify the magma, bring it to the surface. In other words, I think we're going to have a Sierra Nevada mountain range to cross between Ellensburg and Seattle 5, 6, 7 million years down the road. That's the major way that I teach this to my students in the national parks class, because many of the national parks of the American West are tied into this story of North America slowly crossing the East Pacific Rise. Now, the plot thickens slightly before we narrow our focus to Mount Rainier itself. Tim Melbourne, this guy that I talked a fair amount about last Wednesday, the guy that was doing the work here at Central involving the silent earthquakes, I just casually sent him an email last night and said, Tim, this is a holdover from last week, but I convinced the group last week that the Juan de Fuca Plate is moving northeast towards Washington. And why did we know that? We had our GPS stations last week, remember? Going northeast and then turning around suddenly for 2 weeks. And then northeast, and basically the compression from the Juan de Fuca Plate is causing a northeasterly trajectory. My question to Tim was, it's always bugged me why the Juan de Fuca Plate is going northeast when the spreading out of the East Pacific Rise off of our shore looks like the Juan de Fuca Plate should be going southeast. Do you see my issue here? Just the geometry here says, isn't the Juan de Fuca Plate going southeast instead of northeast? And he said, well, first of all, you're wrong. That's always a nice way to start an email, isn't it? Nick, hi Nick. First of all, you're wrong. So I kind of knew I was wrong, but I wanted the full story. And I'm not going to go through it because it gets into how the plates are moving with respect to a neighboring plate. If all these plates are moving, you have vectors of motion, and it's hard to pinpoint exactly who's doing what, because it's all this relative motion jostling next to its neighbor. Tim's basic message was, he says that this spreading center here, the East Pacific Rise, is not fixed. In other words, this boundary is not as permanently located as I'm presenting it. He says the East Pacific Rise is drifting northwesterly with the Pacific Plate. In other words, the Pacific Plate is dragging this plate boundary with it. And if you work out the vectors of that and us coming actually southwest, that was part of our story last week, you can complement the vectors and get a northeasterly direction. Okay, so I have two choices as a teacher, right? I can pretend I never had the email with Tim, and I can continue with what I've just taught you, which is what I teach in my 102 class, or I can try to get into these different vectors and try to give the real story. I'm torn between the two. I gotta be honest with you. This is a very simple story, and it appears we're making headway on getting rid of the Pharaohs Plate. So I'm stubborn right now, 12 hours after getting the email, to think that I might still be right, that we're going to get rid of the rest of the Juan de Fuca Plate before it's all said and done. But if Tim turns out to be right, this spreading ridge is actually going to drift away from us, and the Juan de Fuca Plate is going to maintain its size. Hell, it might even grow in size if we're taking this ridge and drift it away from us faster than North America is moving west. Okay, so now we're officially on a tangent. How's it feel? We're way off track. All right. Students hate that, right? Here's what we're doing today, and then I'm off on something else. And am I supposed to write this down? Is this going to be on the, Okay. So, it's my lecture, damn it. I'm saying Mount Rainier is going away with the rest of the Cascades because of us finishing this job. Okay, let's get something a little less controversial and talk about the Cascades themselves. So, time to look at my notes quick. Yep, that's what we're doing. Good. You know what this is by now. This is Washington. Of course it is. Let's put Ellensburg in. Let's put Seattle in. Let's put the I-90 drive between Seattle and Ellensburg. Okay, I-90. Terrific. We have 5 active composite cones in the state of Washington. Let's put them on the map. Mount Baker, Glacier Peak, Mount Rainier, Mount St. Helens, Mount Adams. Okay, we got 5. We got 5 mountains that have the possibility of erupting starting tomorrow. And with our understanding presently of the Cascade volcanoes, all are possible to start rumbling tomorrow. And the good news is, with these types of volcanoes, we usually have multiple weeks of small events before something big. And that is a comforting thought, that it does not appear, based on composite cones around the world in the last 150 years, doesn't appear that Rainier is just going to go bang tomorrow at noon with no warning whatsoever. We'll get swarms of small earthquakes. We'll get changes of the slope of the mountain itself. We'll get dramatic heat changes at the top of the volcano. Glacial melt will start more dramatically. We'll have changes in the gases at the summit. In other words, we'll have all these small things, and if you're a sane person, you'll get out of harm's way, and the mountain will do its thing. Okay, so how long have we had the Cascades in general? The answer is 40 million years. How long have the Cascades been in Washington? 40 million years. Now, what I mean by Cascades is this corridor of active volcanism. But I'm not saying that Mount Rainier has been standing for 40 million years, or that Mount Adams has been standing for 40 million years. Instead, this corridor, this little ribbon of active volcanism that we call the Cascades, have been active for 40 million years. Why not back to 200 million years? That's going back to our first lecture of this series, where we're bringing in pieces off the ocean and building Washington. It's not till 40 million years ago that we had this be the appropriate place to start sending magma up from the subduction zone. Okay, so 40 million years. Now here's what I think is really interesting and not as well sold to geology students around the country or around Washington. If you start digging deep and looking in this corridor between our 5 active volcanoes, it suddenly becomes very clear that we have, and I'm not exaggerating now, hundreds of old volcanic centers. What I'm drawing here in blue X's are inactive cone volcanoes. In other words, places where Mount Rainier-like mountains used to stand, used to erupt, and lost its magma supply and has been eroded away. And then a neighboring cone grows, beautiful, nice and big, erupting material, looks like a national park, loses its magma supply, goes away. We literally have a graveyard of volcanoes in the Cascades. And there's only 5 current places where we have volcanoes that are alive. Mount Rainier has only been standing at its spot for less than 1 million years. I'll give you an actual number. 500,000 years for Mount Rainier. We've had volcanoes in central western Washington for 40 million years. Our present guys have been there for 500,000 years or less. St. Helens is even less than that. So when I say that Mount Rainier is not always going to be on the horizon, I mean it. I mean, forget about the debate about whether the Fuca plate is going to get destroyed completely or not. Even with our understanding of this, it's pretty safe to say that Rainier is not going to stay that long. My number here, I'd say the average lifespan for a Cascade cone volcano is 2 million years. You have it born, you have it nice and beautiful in adolescence, it slowly starts to crumble away as we get older, it's gone, okay, that's it. A 2 million year lifespan for a cone in the Cascade corridor, and we're a quarter of the way through the life cycle for Mount Rainier. These other places are places you know. In other words, where the blue X's, they're locations that you might know. If you've hiked in the Goat Rocks, if you've hiked up, take your pick. I don't need to go through. Take your any favorite place up in the Cascades that's not these 5 red X's. I'll be willing to bet you there's some old igneous rock nearby that's basically the old plumbing system of that volcano. The structure is gone, but the underground magma has cooled off, and we can reconstruct where that magma was. There's some researchers still working on these problems. Paul Hammond is one of them, a retired geologist from Portland State, has been working in the Mount Aches and Goat Rocks and other places basically on the way up to White Pass. But that's just a local example. There's lots and lots of great examples of this. So that's something we want to work on and try to understand. Good. On to the next topic. Some basic stuff, and then we'll try to speculate what's coming down the road for our lecture. I've been having an internal debate in my mind as I've been talking the last 10 minutes. I don't know if you can tell. And I just decided, I got to tell you this story, okay? My office this afternoon, one of my freshmen getting ready for the midterm tomorrow. She knows that geographic examples are very important of geologic concepts. So if we talk about a divergent plate boundary, it's equally important to know a couple of places in the world where they exist. So she's a hard worker. She's in there in my office hours. I give her credit. Let's call her Julie. And Julie opens with this question. I'm having trouble with geographic examples. Where are the Cascades? All right. And I said, Julie, we can figure this out. Where are you from? Federal Way. Julie, you going to go home this weekend? Yep, I go home every weekend. You got your own car? Yep. You going to go over the pass? Yeah, I'm going to go over the pass. You going to go over those mountains? Yeah? Right. Julie, are you... She wouldn't take the bait. So, those are the Cascades, Julie. Those are the Cascades, that mountain range. It's right there. You drive over the Cascades every weekend. So she wrote it down. She's got it now. All right. Okay, let's say you're a composite cone. I don't care if you're in the Cascades or in the Andes or in Japan, Fuji, composite cone, Kilimanjaro, Africa, composite cone. I don't care who you are. You have the capability of producing 4 different things when you erupt, Mr. Composite Cone. And I guess I'm going to do the same thing I did just before. I'm going to do a cross-section of the cone, and I want to draw a national park boundary, and I want to look down on top of that composite cone. Okay? And since you're not being tested, I'm not going to bother writing these names down, but I'll just give them to you verbally. Number 1, we're going to get a bunch of volcanic ash that's blown downwind, and we're going to have that ash fall onto the landscape. So, I'm going to change my picture so we can actually have an ash column. So here's our towering cloud of ash. You can think Mount St. Helens in 1980 if you like. And then the prevailing wind is going to take our ash downwind, and we're going to literally snow that ash down onto the landscape and create a blanket, a layer of ash. That's ash fall. Now let's just presume there's westerlies on that particular day, and so we're going to have this cone of area that is to the east of the erupting cone. If this is Rainier, and this is Rainier National Park, this is us, friends. If we're talking about volcanic hazards, it appears that's our likeliest candidate for experiencing Mount Rainier when it erupts. An enormous amount, I don't know what that means, enormous by the way, we'll talk about that before we quit. A lot of ash if we have westerlies coming across Rainier. Okay, second of all, what do you get? We're going to have some ash flows, not the same as ash fall. So ash flow is the most dangerous. 100 miles an hour, white hot, a traveling cloud of ash, rock, gas, logging trucks, anything it picks up along the way. And this is a ground-hugging cloud that is not deflected by any topography. So if there's a ridge in front, that ash flow is going right up and over that ridge and continuing. So we're going to basically get our momentum from that, oftentimes by the column collapsing on itself, and having much of this material literally get a head start before it starts cruising over the land surface. You do not want to be in the path of one of these. Got some video for you in just a bit. So that could be any particular trajectory coming away from the composite cone. Really no good way to predict the direction that that's going. And if this is Rainier, we have ash flow deposits not far outside of the national park. So Ellensburg does not have to really worry, in my opinion, for ash flow material because of our distance from the cone and because we don't have any pyroclastic flow deposits in Kittitas Valley or ash flow deposits. That's the best way to judge volcanic hazards, is to look at what's underneath your ranch. Has it happened before? Has something gotten to your ranch before? Ording, Puyallup, that's coming in a second. So if there's stuff underneath your town from an erupting volcano in the past, we're going to increase our chances, obviously. Third of all, we're going to have lava flows. And most of us think of lava flows coming away from an erupting volcano as being a very hazardous thing. But hey, these are sticky lava flows with cone volcanoes. These are not Hawaiian lava flows that flow for tens of miles, or the flows that came across eastern Washington. That's basalt. This is andesite. This is stickier, higher silica magmas that are more viscous, not wanting to travel. So again, it's a comforting piece of news. If you visit Rainier Park, the lava flows are as plain as day when you look at a geologic map. In fact, if you can visualize in your mind your trips to Rainier, there's kind of a radiating set of ridges that go away from the mountain itself. Each of those ridges is an old lava flow that didn't get much further than the park boundary. Finally, mud flows. Most of you have heard this story. The mud flows are the real threat to residents of the west side, not so much us here on the east side. And that fourth one, the mud flows, were not even really understood until the 1950s and 60s and 1970s. And that's part of the video clips that I want to show you tonight. Some really great work. We had real imaginative work from Brian Atwater a couple weeks ago, imaginative work for other people. The hero tonight is a guy named Rocky Crandall, who back in the 50s and 60s worked for the U.S. Geological Survey and was the first to kind of be creative enough to see deposits and realize, my God, these are actually flows of mud traveling tens of miles from the mountain, leaving the park, and getting down to the Puget Sound. Many large communities now built on those old mud flows. So the good news there for predicting mud flows coming away from the cone are the mud flows are following river valleys. So we can predict the paths of those mud flows simply by looking at the drainages coming away from the mountain. So here are our active drainages coming away from Rainier. Again, there's good news for Ellensburg. The crest of the Cascades, the topographic high point in the Cascades that Julie now knows and has in her notebook, is protecting us from even these mostly dreaded volcanic mudflows, otherwise known as Lahars. Even these drainages coming directly east towards Ellensburg, the mudflows are going to follow the drainages and eventually head westward. So we're really in good shape. And I might comment while I'm thinking about it, we haven't maybe found all of the ash deposits in Kittitas County, but I'm guessing that we've run into the major ones, and there's really nothing clear connecting the Kittitas Valley with Rainier Park. Before we go to the slides, I want to give you a sense that our main understanding of the history of this mountain is looking for all of the ash falls from past eruptions, all of the old mud flows from past eruptions. And we have precious little on this side of the crest from Rainier. In fact, we have precious little, period. We've got a famous ash layer down in the canyon that's typically attributed to Mount Mazama down in southern Oregon. We have a beautiful, about 6-inch volcanic ash layer in Craig's Hill, right above the fairgrounds, that's been studied, and it's much older than Rainier. It's a few million years old. Unknown which volcano erupted. So there's teffers out there, there's ash layers out there that just haven't been looked at very carefully, and that's one of my main messages tonight. Well, there's plenty more to learn about the history and potential eruptions in the Cascades because we haven't had the man-hours invested in all of these ash deposits. So for the rest of tonight, before we go to the technology, I want to talk about number 1 and number 4. The ash fall coming downwind, and the lahars, or the mud flows, coming down the river valleys. And I want to give you a sense of what was discovered back in the 60s and how that has changed in the last century, in the last decade, how that has changed in the last 10 years, and how we've got a better but not complete view of what has been going on with Rainier through time. Normally, when I teach, I like to have a conversation going with the group, and we have plenty of back and forth. But we're in a well-worn groove right now. We want to make sure that we get through what I have planned, and then there's plenty of time after the lecture to follow up with questions. So let me summarize the best we can. I tried to come up with a creative way to present this, and I ran out of creative ideas. So I think I'm just going to write a few things on the board for you, just to give you a sense for how much we know about the history of eruptive activity recently with Mount Rainier. It's currently active, meaning it has magma inside of it. The magma is hot. There are 30 small earthquakes per year with Mount Rainier. 30 quakes annually with small motion of magma within the magma system. There's continual heat transfer to the top of that mountain. In fact, if you've ever been to the top of Rainier, I haven't, but if you have, or if you've seen photos, there's some beautiful summit craters, and the rims of those craters are snowless. You know that most of Rainier has thick cover of glacial ice. But even after a big blizzard, a few days later, that snow is gone up at the summit craters because of the heat coming off of that radiator. So it's a throbbing, heat-filled structure. There's no question about if it's going to erupt based on the history I'm about to give you. So I'm going to put his name on the board. Rocky Crandall, Dwight I think was his given name, Dwight Crandall, and another guy, Molyneux, forget his first name, pardon me for that. Back in the 50s and 60s, they did the groundbreaking work on looking for ash fall deposits and lahar deposits from Rainier. This is all Rainier now, in Rainier Park. They dug a famous trench right next to the Sunrise Visitor Center. Been up to Sunrise? Okay, you can picture those beautiful parks that are up there. Okay, I've got one slide in particular that shows just one simple ditch that they dug, one hole that they dug, looking for ancient ash fall deposits from Rainier. And they got ash falls that they could date. You take some of the ash, you send it to a lab, they do some absolute age dating, and they come up with a numerical date for that particular ash. 1840 AD, 1479 AD, 190 BC, 500 BC, 700 BC, 15 BS. I just wrote BS. It might be BS. 1500 BC, 3600 BC. I'm not going to go on forever. I want to give you some of these landmark ash deposits. 2, 4, 6, 8, 9. I think there were 10 classically found ash fall deposits at sunrise, right there on the mountain. And they weren't hard to find. You know how science works, right? The first time you look, you find the most obvious things. Then somebody else comes in and they find the less obvious things. These were actually given letters. So in the literature, there's actually letters corresponding to these particular ash layers. The letters correspond to the locations that they were found. Now this looks like a history of Rainier. We're in Rainier Park, right? We're finding ash deposits in Rainier Park. It must be Rainier ash. It's not all Rainier ash. So not only can you get ages, you can get chemistry of the ashes. And you can match chemistries. In other words, you can find this ash layer and say, does this chemistry of this ash match Rainier's chemistry, or does it match St. Helens? So let me add that. Rainier, St. Helens, Rainier, Rainier, St. Helens, St. Helens, Rainier, Mazama, the famous Crater Lake explosion of 3600 BC. Oh, sorry. I'm off. Rainier, Mazama, and Rainier. This will play real well on TV, by the way. Okay, great. St. Helens is just next door. We get a significant St. Helens eruption, we're going to blanket Rainier with ash. I never thought about that till I started reading some of this stuff. So I'm not asking you, like we did with the Chris Goldfinger lecture, to look at the average number of years between ash layers and come up with a recurrence interval. That's what we did with those underwater landslides, if you recall. Why am I not doing that here? Because this is just the 10 most obvious ash layers. The work that's been done in the last 2 decades by some other folks, Tom Sisson, a few other guys, Jim Valance, some other folks I haven't met, Pat Pringle. I'll just cut to the chase. They now have 40. So here were 10 ash layers in Rainier Park, not all of them from Rainier. There are now 40 clear ash layers with ages, most of them attributed to Rainier's eruptive history. And maybe more importantly for us, the kind of take-home message from that is we have 12 Rainier ashes since 500 BC. That's a more accurate representation of the last 2,500 years. And if that's a complete representation, maybe we can start doing recurrence interval talk. A little early for that, though, probably. While we're doing this, let me give you a few more, and then we'll go to the visuals, because then it just becomes me listing stuff up here, which is not that fun. This is all ash. These are all fine layers of ash blown downwind and deposited, snowed on the landscape. Lahars, remember, are different. I'll have some video for you, but to prime you for this, Lahars are the result of a flank of the mountain moving, landslide, convert that into a flow of debris. So we have a side of the mountain that has what? Glacial ice, it has snow, it has water, it has rock, it had ash, it has lava flows. It's got a visitor center on it, maybe. People. Let's not put that in there, okay? And then we have this event. Maybe an earthquake triggers the mud flow. Doesn't have to be an eruption, but most commonly it's an eruption that triggers a failure of the flank of the mountain. And we have that material have so much moisture in it, so much water in it, that we can actually convert that landslide into a flow and have that material start sailing down a river valley. The consistency of concrete, wet concrete, stuff in a cement mixer, 40 miles an hour, 30 miles an hour, coming down a river valley at you, it's a hazard. It's a problem. Many of you know of the hallmark, the most famous mudflow, probably in the world, but at least in North American geology, involving Mount Rainier. The Osceola mudflow, date 3600 BC, 10 times bigger than any other Lahar deposit in the Pacific Northwest. So this was a monster. It actually reduced the summit of Rainier by more than 1,000 feet. So Rainier used to be taller by an extra 1,000 feet. So the top part of Rainier converts into one of these flank landslides, and the scar is still at the summit of Rainier. I'll show you in a second how to find that, how to look for it. That's the mudflow that eventually got to Tacoma. And that's the mudflow that Tacoma, Auburn, Puyallup, Ording are built upon. And there is real concern of a repeat performance because the mountain has rebuilt itself, and there's some real cause for concern. I'll let the video speak to that. That was probably Rocky Crandall's single claim to fame. Visualizing that deposit was a mudflow, realizing that it was this coherent event that happened at this time. There are some lesser known mudflows or lahars, including the electron mudflow that happened about 500 years ago. We now have, again with current work, that's the theme we're working on with this spring. No, this is fall. That's the theme we're having this fall. Current work, adding to known stuff. We now have 50 lahars. 50 lahar deposits from Rainier that have been found and have been mapped out. Unclear to me if the ages have been assigned to all of those yet, but we have at least 7 lahars since Mazama. So since the Crater Lake explosion, we have clear evidence of 7 lahars sitting on top of that Mazama event. Simple picture to start with. Many of you have seen this before. Subduction zone, fueling magma into our system here. Go ahead, Eric. When we cool the magma off underground, that's our granite formation. When we get the magma to the surface and have an erupting volcano, that's andesite. And Marty, I'm saying that as soon as we have North America cross the mountain range that's sending stuff our way, there is no more stuff coming our way. So we're going to get rid of this subducting plate, and the subducting plate is the only reason we have volcanoes to begin with. Next one, Eric. Okay, here's a map of the East Pacific Rise. Can you find it? Here's North America, South America, and right here is still the East Pacific Rise. But notice where it goes. Right into the Gulf of California and disappears. Next one, Eric. East Pacific Rise disappears. We've crossed it, except for a little piece of it right out here. That's our own special little East Pacific Rise, making our own little Juan de Fuca plate. Notice South America still has all of its volcanoes because it isn't even close to crossing the East Pacific Rise. So this was us back 40 million years ago. Now this is us today, crossing the finish line like the end of a 100-meter dash. We're crossing the tape. Next one. So down to California, what does it look like? Here's us and our active volcanoes. Here's the Sierra Nevada range where the volcanoes used to stand. Why don't they get volcanoes anymore? There's no more subduction. This is the Pacific Plate heading towards Japan, fueling Fuji. And so next one, Eric, if we go to the Sierras, it's all granite. The volcanoes were here, they're up in heaven, literally, they're gone. And even Half Dome in Yosemite Park is granite, magma that cooled underground. Next one, please. Here's an animation showing North America crossing the East Pacific Rise and getting rid of our volcanoes. This is the last 40 million years of time. Some of you have seen this one before. Let her roll, baby. There we go. Okay, so this video looks like that the East Pacific Rise is moving towards us, but what's really happening is North America is crossing over the East Pacific Rise. And notice here's our Juan de Fuca plate. And actually, I'm curious to see how they're showing these specific. Yeah, they are seeing it more. Yeah, okay, whatever. Tim's right. Tim's right. Okay, next one. All right, here's the Juan de Fuca Ridge. Here's our small little plate. Notice that the north-south distance of these little slabs of what's left over from the Farallon controls the north-south distance of these cones. You get south of Lassen Cone, there's no more volcanoes because there's no more ocean crust coming at us. The yellow are the old Cascade deposit, in other words, the graveyard I was talking about. Let's look at that a little bit. Next one. So here's Hood, Adams, St. Helens, Rainier, Glacier Peak, and all this light green are older volcanic deposits where the old volcanoes used to stand. Next one. Same message. This is from an excellent book cranked out 2 years ago by Pat Pringle. It's the Roadside Geology Guide to Mount Rainier National Park. It's a spiral-bound thing. If you've used a roadside geology book before, you know it's kind of fun in a weird, nerdy sort of way. I recommend this. This is 2 years ago. There's a lot on here. Can I convince you what the main message is? Here's Rainier. Here's St. Helens. Here's Adams. And all these colors, old volcanic centers. Again, these are places where cones used to stand but have crumbled away, but we've mapped them and I've identified them by age. Everybody's less than 40 million here. Pretty spectacular. Next one. Yeah. So I have a way to tell my students how this works. You've got the Cascades for 40 million years, but you don't have actual standing volcanoes for 40 million years. We only have a 2 million year lifespan, right? So this is at the county fair, a game called Whack-A-Mole. And so you whack one mole and you think you've got it, but then another mole comes up, and then you whack that mole and two more come up, and then you whack those and then two more come up. That's the history of the Cascades. Next one. Whack-A-Mole. Now comes another cone up next door. Next one. Whack-A-Mole. We got rid of these. Here comes another one. 2 million years, boom. 2 million years, boom. You got it? Okay, next one, please. So, to Rainier we go from Tacoma looking southeast. Next one, please. The insides of these cones are complicated. They're not all lava flow layers because of those 4 possibilities we talked about. Ash fall, ash flow, lava flow, mud flow. It's a combination of things. So the next one is an animation showing some of these in action in kind of an animated, cartoonish way. Next one, Eric. Oh, sorry, it's not. Here's just a chart showing that Rainier got its start 500,000 years ago, and the whole structure has built just in that last 500,000 years. Next one, please. Oh, I don't know where that movie is. Maybe I took it out. Here's Pringle's roadside book. Highly recommended. I can help you later on if you want to find it. Next one, please. There's Pat himself. Fine fellow. And Bob Butler is included. He was one of the main paleomagnetic guys who didn't like the Baja BC story that we told on our first lecture. Next one, please. Here's an interesting chart that you may have seen before. Each of our 17 cones in the Cascades and our current understanding of how often they have been active in the last 4,000 years. So St. Helens has been very, very active. What is this based upon? Ash falls, Lahars, the things we were just talking about. And to be honest, my gut feeling is Jefferson, for instance, is naked here. Adams only one. I don't think they've been that quiet personally. We just haven't found the deposits yet. That's my take. But as our current understanding, this is the way we view the history of all 17 of those cones. They're all being fueled by the Juan de Fuca Plate subducting. Next one. Here's that movie. Let's play it, Eric.
Stratovolcanoes are built from alternating layers of pumice and ash, or lava, produced by many different eruptions over tens to hundreds of thousands of years. The volumes of individual eruptions can be small to large. The magmas have moderate to high viscosities, but a range of gas contents. Gas-rich magmas commonly blast high into the atmosphere. Pumice and ash fall from the eruption cloud, adding a new layer to the cone itself and blanketing the surrounding landscape. Magmas with low gas contents produce lava flows. Some lavas erupt from flank vents. Other lava flows erupt from the summit crater. Because the lavas are fairly viscous, they don't flow easily, tending to perch on the sides of the cone and helping to give stratovolcanoes their relatively steep profiles. The most dangerous types of explosive eruptions are those that generate pyroclastic flows. The ejected pumice and ash fall back around the edges of the eruption column and feed hot clouds of pumice, ash, and gas that move rapidly down canyons on the volcano's flanks at speeds of up to 100 kilometers per hour. When most people think of a volcano, they envision a stratovolcano. Well-known examples are Mount Fuji in Japan and Mount Rainier in Washington State.
Okay, so if we take a peek in the flanks of Rainier, we're now up climbing or using helicopters to get up on Rainier itself, and looking at the rock exposed between glaciers, we're seeing it's not a simple story. It's quite complicated. Next one, please. And I want you to just notice that there's a variety of looking things in here. Not all the same stuff because of these different products. Next one. Here's a person standing next to a particularly ashy layer. And then here's more, maybe an ash flow tuff or one of those ash flow deposits coming on. So the history is laid out there for us. We just have to look at it and read it properly. Next one. Here's some Tom Sisson slides. I find this particularly cool, that there's a huge pumice layer from 195,000 years ago making up the wall. So sometimes these layers just hit you over the head. Other times you have to work very, very hard to find them at the flanks of the mountain. Next one, please. I got a few more slides here. I got 8 o'clock. I heard a couple beeps. Your watch is going off. You got 10 more minutes? Yeah. Okay, let's go for it. So keep it going, buddy. All right. So this is not Mount Rainier. This is in the tropics somewhere. Concern. In the park. Not concern for Seattle, not concern for Ellensburg. This is ash flow coming right at you. Next one, please. Okay, more on Rainier itself. Next one, please. Here's a nice shot looking at Ording, the Carbon River, the Puyallup River, and Rainier. What makes up this valley floor? Mudflow. This is the main contribution back in the 1950s and 60s from Crandall. Next one, please. So the Lahars, as we mentioned, are often converted landslides, although sometimes it can literally be mobilized material coming from an erupting column. But the point is, it's a slurry of water and rock that has potential danger as well. Next one, please. So here's a video clip of Rocky Crandall himself. I think he passed away recently, unfortunately, but this is from a DVD that's now out of print called Perilous Beauty. I think it was cranked out in '96. Next, go ahead and let's activate this.
But most important to us are the sudden landslides that every now and then tear away vast portions of the cone and send massive mudflows thundering down its valleys. Many have traveled tens of miles, all the way to the Puget Sound lowland. Development is now crowding into these same valleys, building atop the remains of old mudflows. What events might affect these towns over the next 50, 100, or even 500 years? Rocky Crandall began to answer this question quite unexpectedly during a study that began some 30 miles from the mountain, on the edge of the Puget Sound lowland.
I was just out of graduate school in the early 1950s, and I was assigned by the Geological Survey to make a geological map of an area east of Tacoma, Washington.
Working from older maps, Crandall expected to find the hummocky remains of glacial deposits around the towns of Buckley and Enumclaw. When he arrived, he found only a flat plain. Where he expected to find glacial sediments plastered on the hills, they seemed to occur only in the valleys. As Crandall attempted to explain how the valley floor had formed, he found himself moving in a surprising direction and toward a stunning conclusion.
And I came up with the idea that perhaps it had actually flowed into place, like a giant mud flow. And it was just like a light going on over my head, because everything I knew about the deposit fit this kind of an origin, that it actually had flowed into place. It had not been formed by a glacier at all. But the question in my mind is, if it is a mud flow, how did it ever get started? Where did it come from? And I had no idea at all. Even though standing there on the plain that was formed by this mud flow, I could see Mount Rainier in the distance. And I didn't make the connection for a long time.
As Crandall searched vainly for the source of this giant mudflow, known as the Osceola, its deposits led him up the White River to a point 10,000 feet up the northeast side of Mount Rainier.
We could hardly believe our eyes when we actually found a remnant of the same deposit there at the tip of Steamboat Prow.
As he stood on Steamboat Prow looking toward the summit, Crandall realized that the Osceola could have come only from the sudden collapse of a major segment of the mountain. This was a radical idea. Such massive volcanic landslides were virtually unknown. That is, until 1980, when the north flank of Mount St. Helens, weakened by rising magma, collapsed in the largest landslide ever witnessed. The landslide released an explosive blast that laid waste to over 200 square miles of forest. And the landslide also spawned a giant mudflow that raged 50 miles, all the way to the Columbia River. When all had settled, Mount St. Helens lay gutted and bare. The upper Toutle River had become a barren and rocky place where craggy fragments of the mountain pocked the surface of the landslide.
So here's our yellow areas where most of this is the Osceola. All these areas here is where the Osceola actually hit and got into the Puget Sound right there at Tacoma. Find pieces of Mount Rainier, literally, in downtown Tacoma, in part of this slide. That was a major contribution by Dr. Crandall. Next one, please. Okay, these are kind of out of, no, they're not. So here's the old rim, basically the scar from the Osceola. In other words, that upper part of Rainier converted into a landslide and flowed, and here's the scar that was left. Can we find that in photos? Keep it going here, Eric. Great, that's out of order. There's the scar.
We now know that the entire summit and northeast face of Mount Rainier fell away suddenly in an immense landslide accompanied by volcanic explosions. The landslide became a mudflow that filled the White River Canyon with up to 600 feet of rock, clay, water, and ice. This cement-like slurry thundered down the valley at speeds up to 50 miles per hour. As the flow left the mountains, it spread out to form the Enumclaw Plain that had led to Rocky Crandall's original insight. Finally, the Osceola disappeared into Puget Sound. It is difficult to grasp the destructive force of one of these massive mudflows.
Great. So here's our scar. Here's lava that has grown since the Osceola. So in other words, Rainier has rebuilt itself almost completely. And here's the former summit before we slid that material away. Here's another try at it, Eric. Used to be a bigger mountain. And after the Osceola was significantly shorter, then we've had the lava dome growth since. A few more and we're done. Another shot, same thing. Looks like a big scoop of ice cream. That's glacial ice that's on top of a rebuilt andesite lava dome in the 5,000 years since this event. Keep it going, Eric. Here's what a Lahar, the Osceola actually looks like. So that's what a mudflow deposit looks like after it comes to rest. Next one. St. Helens, we're talking about ash now. Oh, I got to get to these. Sorry about this. This is running a little longer than I wanted. Go for it. So here's Jim. Look at all these ash deposits. Age for each of these ashes, some of them Rainier, some of them St. Helens, some of them Mazama. Next one. So here's Rocky's pit right at sunrise. Each of these letters corresponding to a particular eruption. Here, O is Mazama, same Mazama we have in the south part of Yakima River Canyon. And each of these guys set up beautifully. Next one. As we get farther away from the mountain, the particle size decreases. You can imagine that, right? As you transport it longer, you're going to have finer material settling out. So we can even work with the size of the particles to make a basic call as to how close we are to the ancient mountain, even if the mountain's gone, like Craig's Hill, for instance. We've got our ash in Craig's Hill, but it's too old to have a present volcano standing. Next one. Know where that is, right? Yakima River Canyon. Mazama ash. There's some other ashes in there as well. There's still some debate about the significance of those. To my knowledge, the only significant ash deposits in the central part of the county. Next one. Older sites also in the park. This has all been grown over now. This is a photo back from the 60s apparently. Again, just giving you a sense of us getting a chronology from those ashes. Next one. Next one. Oh, good Lord. Next one. Last thing, and then we'll quit. There's geophysical work that's been done on the west flank of Rainier. West flank. Most of the folks working on this think that the west flank of the mountain is the most likely to go, is the most likely to fail. If there is a next mudflow coming in the next 100 years, they expect this side to go. And I have to show you the video clip going with this. Would you mind? Let's do it. Next one. Here it is.
Many of the ridges low on Mount Rainier are formed of massive lava flows up to 2,000 feet thick. But high on the mountain, thinner, steeply sloping layers are much less stable. Lava cliffs 50 to 100 feet high are separated by beds of rubble, fragmented pieces of lava that are soft and easily eroded. These rocks could break loose at any time, nudged, for example, by a large regional earthquake or a steam eruption. Mount Rainier is weakened even further by hydrothermal alteration, a process that turns solid rock into soft and slippery clay. Atop the end of the Tahoma Glacier, in a landscape of altered rock, the smell of sulfur taints the air. Boulders fall apart. Iron minerals crust the rock like rust. Slippery clay minerals coat the volcanic debris. In the early 1900s, this material fell suddenly onto the Tahoma Glacier from Sunset Amphitheater. Here, this 600-foot cliff has been transformed from hard lava into a crumbling mass of weak rock by hot acid water moving through the volcano. This chemical transformation requires water and heat, which travels from the magmatic heart of the volcano. Water is present everywhere on Mount Rainier, released by sun and rain.
Great. So, there's much work to be done. We need to learn more about the history by studying more of these tephras. We need to do more geophysical work to get a sense if the west flank is really the next to go. And these conferences I've gone to the last couple of summers has been with middle school teachers to try to educate the public, mainly on the west side, to understand the risk, to practice evacuation drills, literally, for some of these communities. And us here on the east side of the Cascade Crest appear to be okay, but as we learn more, like with earthquake stuff, as we learn more, we become less and less confident that we're as safe as we thought we were. Thanks so much for coming out tonight. Really appreciate it.